Having talked about the kinematics of circular motion, now we'll talk about the dynamics of circular motion, i.e. how do forces apply. Alright, here we're going to do an experiment where we roll a ball around a track and want to see what comes out next.
Here I have a circle with the segment of the circle removed, and I'll roll the ball in the circle like so. Now the question is, which can will the ball hit when it exits the circle? Will it roll around to hit the yellow can? Will it continue in a straight line to hit the white can? Or will it continue in a circular path to hit the green can?
So, take a second.
All right, let's roll the ball
and see what happens.
So as you can see, it hit the white can. While the ball was in the circle was keeping the ball in a circular path. Once the ball left the circle, there was nothing to act on the ball to keep it in a circular path, and the ball wanted to continue going in a straight line.
In essence, that was a statement of Newton's first law and then second law, which is that when there was no longer anything pushing on the object, it would go along a straight line in a constant speed, and therefore when it was running into the wall had to push on it to make it go in a circle. For an object to travel in a circle, there must be an acceleration on it towards the center, which means there must be a net force which points towards the center, or really at least that has a component that does. We call that the centripetal force. But be careful, this is not a new force, it's not a new physical thing, it's not a thing you'd ever put on a free body diagram. It's a shorthand for the net force towards the center. You should always be able to identify the agent or combination of agents that provide this force. Because of this, the centripetal force never appears on a free body diagram. It's not a physical force acting, it's just a mathematical sum of forces. Also, as the aside here, the reason for this little caveat is that if the object is getting faster or getting slower, then there would be a component of the net force along its motion, or opposite to its motion. And so the net force might not point directly towards the center, but there will always be a component that points towards the center. And we'll know the size of the acceleration that is needed. So, a ball at the end of a string is being swung in a horizontal circle. What force provides the centripetal acceleration of the ball? And here we're pretty clear it's going to be, since it's a horizontal circle, it's going to be the tension in the string that does it. Same situation, a ball at the end of a string is being swung in a horizontal circle. What's the direction of the net force on the ball? And we know that the net force would have to be towards the center. This is assuming that the ball is traveling at constant speed around that circle. It's important to understand that that does not mean that the tension points towards the center. Why? Because if we think about it, if we draw a free body diagram for our object, and let's say we're at the moment where the acceleration has to be this way, so we're in a circle that has come out of where the thing is pointing, say, out of the page at us, then there's a weight which points downward, so the tension must point both a little bit upward and inward, and so the tension has to point something like this. It wouldn't be possible to have the tension be horizontal because then there'd be nothing resisting the gravitational force, and the acceleration would have a downward component, which we don't want it to do. An ice hockey puck is tied by a string to a stake in the ice. The puck is then swung in a circle. What force is producing the centripetal acceleration of the puck? And here we see, again, it's the tension in the string, because it's the part that is pointing inward. We need the acceleration to point towards the center, and the tension is the only thing pointing that way. Right, a coin is rotating on a turntable. It moves without sliding. At the instant shown in the figure, which arrow gives the direction of the coin's velocity? We're looking from above here, obviously. The coin is going to move tangent to the circle it tracks out. It's going to track out a circle which is concentric, but somewhat smaller. And so that's going to be the velocity. So A is our direction. The same situation, which arrow gives the direction of the frictional force on the coin? And this one's a little tricky. As our thing tracks out its circle, it's not a great circle, but something like that, there must be a acceleration which is towards the center. And therefore the frictional force must also point towards the center, So it must be answer D. You might find that very bizarre, because you're like, but wait, it's moving in direction A, and why doesn't friction oppose the motion? But friction doesn't oppose the absolute motion, for which there is no definition. It opposes relative motion between the coin and the turntable. And the turntable is also heading in direction A at that moment, at that spot. And so, therefore, there's no need for a frictional force there because they're not tending to slide that way. On the other hand, the turntable will be curving around. The point that under the coin will be moving in a circle, and there'll be frictional forces to keep the coin from sliding relative to that, which means they'll have to point in the center in the same way. Same situation again. At the instant shown, suppose the frictional force suddenly disappeared. In what direction would the coin move? Well, it's going to move in the direction of its instantaneous velocity, which is that way, and therefore it's going to move in direction A. All right, finally done with that coin for a bit. Different problem. Engineers design curves on roads to be segments of circles. They also design dips and peaks in the roads to be segments of circles with a radius that depends on expected speeds, and other factors. Here we have a car moving at constant speed and goes into a dip in the road. At the very bottom of the dip is the normal force in the road on the car greater than or less than or equal to the car's weight. Well, let's draw a free body diagram. We have a gravitational force pulling down, and we have a normal force pushing up, and we know that the acceleration is towards the center of the circle, so the acceleration is up. And since the acceleration points in the direction of the stronger force, it must be that the normal force is greater than the gravitational force. So it is greater than. Here is a professionally drawn free body diagram. Gives us the same idea. Of course, I don't really like these names, so I'm going to change them. All right, the Earth's radius is 6.4 times 10 to the 6 meters. This has been known since ancient times. Assuming the Earth is kept together by its gravity, and of course the surface gravity is 9.8 meters per second squared, what is the shortest day that the Earth could have? In other words, what's the shortest number of seconds, all right? Because here we're saying the shortest day in seconds that the Earth could have. By comparison, a normal day is 86,400, and the question is it much more or much less than that? We'll need the gravitational force to provide the centripetal force. Why? Because of this assumption that the Earth is being kept together by its own gravity. So then we just kind of walk through a calculation. If the centripetal force comes from the gravitational force, and we had an expression for the centripetal acceleration, right? This is ma. You might remember we had the acceleration. We found the acceleration was v squared over r, of course, but we found that we could also write that as 4 pi squared over t squared times r, or 4 pi squared f squared times r. So we go back to here and we say, well, let's use that t squared one because we know the t, or we're looking for the t really, and we know everybody else. We solve over and get t squared is this stuff, 4 pi squared r over g. We do a little bit of arithmetic, a little bit of algebra, and we find that the period is 5,078 seconds, or just about 1.5 hours. All right, clearly our day is longer than that, so the Earth is not held together by just its gravitational force. All right, there are other forces involved that are doing this. We'll return to this number later in the unit.